right away start a new session, which I think is the most important session in this course about transformers. And the reason why this is the most important is that transformers or the architectures that are built on top of the transformers or based on the transformers are now behind the revolution that we see in AI and in deep learning. So I hope that you will get a good idea of how transformers actually work with this session. Transformers started to exist in the area of natural language processing. Natural language processing is about processing and analyzing, understanding the natural text, the text that is written by humans, to do many tasks, okay, like translation, like question answering, summarization, spelling correction, grammar correction, essay scoring that you will see in the project. So many NLP tasks that we actually see in our real life, and the research in this area is not new. It's more than maybe 50 or 60 years back. But the breakthrough that we got recently was mainly one of the major factors behind it is the transformers architectures. So let's see how transformers actually work. And this is all started with a research paper. Has a very nice, I think one of the nicest titles that I have ever seen in research, called "Attention is All You Need." This paper started the idea of the attention that we will inshallah talk about today, and it introduced the concepts of transformers. Okay, so in this session, inshallah, we'll start with motivation, why we need a specific architecture to handle text, and then we will talk about, inshallah, the core idea or core technology behind transformers, which is called dot product self-attention. We will get, inshallah, into details there. We will mention some extensions to it, and then we'll talk about how to put pieces together into what we call a transformer layer. That's, inshallah, I hope maybe today as much as we can. And then next time, inshallah, we'll talk about NLP pipeline. We'll talk about more architectures that are part of the transformers family. And finally, we'll talk about large language models that we see nowadays. Motivation. If we are given a piece of text like what you see here, and we want to design, let's say, this is I think a review, and we want again to do sentiment analysis. We want to see if this review is positive or negative. Okay. All of what we learned so far in the course is what? Is about what? Neural networks, right? So think with me, how can we process such text using neural networks? For anything. Can we provide the text to the network? In neural networks, if you remember, it takes what? It takes what? What is the input to the neural network? Always. Numbers. Okay. Can it be something other than numbers? If you remember in the first week, I told you everything is an equation, right? How can you provide the words in an equation? Okay. So, khalas, done. We'll not be able to use neural networks to process text if we use the text, if we use it as words. So we have to deal with that somehow. Okay. Neural networks use numbers. So the solution is convert text into numbers. Right? Easy. Right? So every word, like the word food here, should be represented as a vector of numbers. Okay. Of course, it shouldn't be just one number, right? We cannot represent a word by just one number, but maybe we can represent it by a list of numbers, maybe hundreds of numbers. Okay, so colors here represent different numbers. So for example, we can have a vector like that. Okay, each entry in the vector is a number. Doesn't have to be between 0 and 1, by the way. It can be any number. It can be positive, can be negative, can be anything. But a list of numbers. Okay, this is called an embedding vector. An embedding vector. So an embedding vector is a representation of a word, or generally we will see that we call them tokens, not words. We'll talk about that later, inshallah. But for now, think of it as each word will be represented by a vector of numbers, and this vector is called an embedding or embeddings vector. Okay? Is that clear? Right. Now we can use it for a neural network, right? If we have a passage like that, then we can stitch together all the vectors for all the words, right? If I have, for each word, I have a vector of length d, and I have n words, then I can have a very long vector that represents the entire text, and the length of that vector will be n times d, right? I have a vector for each word. If I concatenate them all, then we will have n by d vector, and that can be an input now to the neural network, right? Done. It's if we manage it to get such representation, and if that representation is really good, then we can feed the entire long vector of embedding vectors to the neural network as an input vector, and we can build the network to do whatever we want, right? Now, before we do that, I said a word now about having a representation that is good. What do we mean by that? What we really mean by that is that if I represent two words that are actually related, the representation of them should be similar. So, for example, two words like queen and king, right? These are somehow related words. So when we represent them each by an embedding vector, they shouldn't have the same embedding vector, but the embedding vectors of them should be close enough, okay, because they are similar words. But two words, give me two random words. Any? Huh? Rent and chair. Okay, although there are some relationship because whatever you rent maybe have chairs. Okay. Red. Okay. Okay. Red as a color. Yeah. Red and chair. Okay. They are not very similar, right? They are really different words. So the representation of them in the vector space, because now we have a space where we represent these vectors, right? In that vector space, the vectors should be far from each other, right? Because they are not related. That's what we hope. That's what a good representation will be, right? Yes. You mean how we will do this representation? No, no, no. Okay, okay. No, no, no. That doesn't mean that this is each number here represents one letter. No, no, no. Okay, it represents the entire word. Okay, no, it's not. It's not based on the specific letters. Usually, it's based on the entire word. Okay, and let's assume that we have a good representation. We didn't say how we got this representation yet. Okay, let's assume that we have this representation, and we will move forward from that. Okay. Yes. A different language or different sentence or different document. Okay. That's a very good question. If we have one representation for multiple languages, two words that have the same meaning should have similar representation. if they are actually exactly the same word with all different senses of the word, then they should have the same representation. But do we really have two words that are 100% exactly the same word? Maybe. Not always, by the way, because there is a chair of a committee. Right? So يعني, we got the idea, right? So if they are really similar, then they should be similar if they are in different languages. But I would expect also a question about being in different sentences, because being in different sentences might have different meanings. Okay, still they might be similar, but not very very similar. Okay, or in that case we might have what we call a contextualized representation. The word has a representation in that sentence that might be different from the representation of the same word in another sentence or another document. We'll talk about that later. But for now, let's assume that each word has an embedding vector, and we learned that embedding vector somehow. Okay. Right. Now let's try our favorite fully connected neural network. Okay, that's all what we learned so far. So let's assume that we will have the input vector here. And let me change now this. Oops, sorry. So we have the input vector here, and we have the output vector here, and this is just one layer. Okay, one fully connected layer as we are used to, right? And I think you are used to this equation, right? What is the meaning of this equation? You saw it, I think, 100 times before. Yeah, the bias plus the weighted the weight matrix times the input, and then this is the activation function. Okay, so this is the standard fully connected layer that we used before. Right. Now assume that this is the input vector, which will be what? Will be the number, the embedding vectors concatenated of all the words in the sentence. Right. What's the problem with that? Maybe you can feed the network all of that and then build whatever layers that we want and train the network. What could be a problem here? How many connections we have here, by the way? Yani if we have just one word here, let's assume that we have, Sorry? I don't hear you. Oh, 36 connections. Yes, of course. Yes, because we have 6 inputs and 6 hidden units. So if we have d inputs here, then it will be d squared. Right? Type. Now, let's assume that we have just 10 words. Each word is represented by 100 embedding vector of length 100. So how many input values we have? 10 words times 100 is 1,000. Okay, 1,000 by 1,000. That's 1 million in one layer. Khalas. and this is 10 token, 10 words, right? 10 words. This is very long. No, of course not. It's a short sentence, right? If we have a paragraph or a document, and this is just one layer. Maybe it's a shallow network now, right? Okay, and we didn't. It's half actually. It's not. We didn't go to the output part even. So that's too much, right? It's too much. That's really, is that practical to have something like that? Just million parameter at least for a sentence of 10 words, something. And even, by the way, the embeddings now are much more than that, much longer than that. Okay, so that's impractical, right? So that's the first problem. So the first problem is that we have very large parameters in this way. And very large parameters means what? Means so many things. Means more time of training, means might have overfitting, so many problems, right? Type. Even if we cope with that, we cannot cope with that text with different length, right? Because as we increase the length of the text, we will have to increase the network, right? Or increase the number of parameters. The number of parameters now will explode even more, right? So these are really big problems, which means that we need a model where parameters or the number of parameters is not a function of the size of the input. Okay, because if it's a function of the size of the input, that means that the number of parameters will get bigger and bigger as we have longer input text. So we need a model where parameters don't increase with input length. Okay, this means that we need to share parameters. We need to share parameters across words. So there shouldn't be some parameters that are concerned with words in specific positions. The parameters should work or should use to analyze the whole text, regardless of where the words are. Okay, we call this parameter sharing. We call this concept parameter sharing. That the parameters should not, the number of parameters should not increase with the length of the input. So we will share parameters across different parts of the input. And we will see how very soon, inshallah. So that's the first concept that we need to achieve, parameter sharing. If we don't have parameter sharing, then we will have so many parameters with very short input text. The second one is motivated with the two examples that you will see on this slide. Look at this sentence. The animal didn't cross the street because it was too tired. Did you understand this? If I told you, it here refers to what? The animal, right? Everyone will agree on that, right? So that means that in this sentence, we want it to really refer to animal, which means that it should be related to the word animal. Or in other words, the representation of it here should be close to the representation of the word animal. Right? How about this sentence? The animal didn't cross the street because it was too crowded. Now it's very clear that it refers to the street. Right? So in that sentence, we want it to be related to the street. We want the representation of it to be similar to the representation of street. We call this concept self-attention. Self-attention. Each word should attend to some other words in the sentence that are related to it. Doesn't have to be one, by the way. But there must be some relationships between the words that we should capture in the representation of the words. Okay, so a representation of that word might be influenced by the representation of these other words because they are related in this sentence. And as you see, the same word it refers to different things in different sentences, right? So the representation of it should be different. And that can, to some extent, lead us to kind of understanding what the sentence is about and the relationships between the words in the sentence. Here's the example of the restaurant again, and if you read the review here, you will find that the word there here actually refers also to restaurant, and you can see even that they are in different sentences. They are not even in the same sentence. So the relationship might be really far. Might be the distance between them, between the two related words, might be very far. Okay? So in this case, the word there must attend to the word restaurant. Okay? In other words, it must pay attention to the word restaurant. Okay? Is that clear? So the conclusion from this is that there must be connections between the words, and the strength of the connections will depend on the words themselves. And given one sentence or one paragraph, a word can be related to other words with different strengths, because it might be very related to one word, less related to another word, and so on. And this is happening in the same context, in the same text. Okay, again, this is called self-attention. And self-attention is a very important concept behind transformers. That's why the paper was called "Attention is All You Need." Right? That's also humans, by the way. Okay. Any questions so far? Okay, very good. Let me then ask. What is the length of the embeddings vector of an input sequence of 10 tokens and 500 dimension token embeddings? You can think of a token as a word, which is 5,000. Okay, very good. Okay, self-attention in transformers is about finding relationships between words. Is that true or false? True, right? It's about finding relationships between words. Each word is related to only one other word? No, doesn't have to. Some words are getting more attention than others. Yeah, so the attention is between pairs of words. It's not about individual words. So we cannot say, مثلا, these two words in the sentence are very important. No, that's not self-attention. Self-attention is the relationship between words. Okay? So if in that case, if I said some words are getting more attention than others for a specific word, yes, this is now true. But in an abstract way like that for individual words, no, that's not what we mean here. The last one, the representation of a word is influenced by the representation of other words. In general, it can be. Why not? Then it has no influence. Still, it's kind of. The representation of a word is influenced by the representation of other words. Maybe this means it can be influenced by other words. Yeah. Some words might not be, but you will see that in self-attention, actually, it has to be influenced by words in the sentence, even if it is the same word, which means here is that it is not influenced by others. Yani a word might attend to itself only, okay, but it has to attend to somewhere. As you will see in the details, it has to attend to some other words. Yes, of course, Mo, to optimize for the attentions that we will see now. Yes, the model has to kind of understand the context of the text. Okay. Any question about that? Clear? Okay. Now I think we are ready to start talking about dot product self-attention. Self-attention. We can think of it as a block, a processing block, where there is an input and there is an output. The input is the input sequence, the sequence of embeddings, of embedding vectors. Okay, and here we will represent it as a matrix, where the columns are the embedding vectors for words. Okay, and rows are the individual values in the vectors. Okay, so here we assume that we have n words. Each word is represented by one vector of length d. So this is one input embeddings vector for one word. Okay, and we have n words, so we will represent it as a matrix. Okay, so it's a sequence of d-dimension vectors of embedding vectors. How about the output? The output is exactly the same structure. Exactly the same structure. So we will also have a sequence of n embedding vectors. What did we get here? What will we do here if that's the case? Actually, what we will do is that the embedding vectors here will be much better than the embeddings vector here. or should be, or hopefully will be. Okay, so the representation that we will have here for the words after we do this self-attention should be much better than the representation that we started with before the self-attention process. Sorry? Yeah, they are the same size, yes. Same size. Same length of the embedding vector. Yes. So basically what we'll change here is the numbers, the values. Okay? So that the words that are related have similar representation, similar vectors than the words that are not related. Okay? Right. Now I think we should get deeper in or dig deeper into self-attention. Okay? Right. So again, it takes n inputs of size d by 1 and returns n outputs of size d by 1. Right. Now you will see that self-attention we will take it over different levels of details. Okay, so we'll start with the level of detail where we will say, okay, self-attention is just 2 steps. Step one, step two, and then you will see that step two has a lot of stuff. So we'll take step two and then we'll get into it. So the first step of the self-attention, you can call it layer by the way, or sub-layer, is to compute what we call values. So we have input vectors, and we will get values vectors, still of the same size, but that's not the output vectors. So you can consider values are intermediate output. Okay, something intermediate that we will need to produce the final output of the self-attention layer. How we will get the values? I think this is very familiar to you, right? Again, we will have a weight matrix and biases, vector of biases, and by doing this operation over one input vector, we will get one value vector. Okay, so here n represents a number, a specific word. You can think of it that way. So for specific xn is the embedding vector for the word number n. Okay, so we will multiply it by a weight matrix, add biases, and that will be the value vector. This is similar to what? This is exactly similar to what we do in one fully connected layer without the activation function. Very good. That's just the linear part. Okay, just the linear part. So there is no activation, no radio, no activation function here. Okay, right. Notice something also different, which is the subscript of the weight matrix and the biases. Look at the weight matrix. What's the subscript here? V. It's not N. Okay. So if I change N here, this still will be the same matrix, which means that the weights and biases here are shared among the words. Same weights, same biases will be used to convert any word, any input embedding vector to any value vector. Okay? Is that clear? Okay. For now, assume that we learned these things. We will not talk about training today. Okay? Assume that we have these things. We need to understand how how self-attention will work with that, and then inshallah we'll see how to train them. Okay, but these are parameters, of course. Weights and biases, of course, as usual, they are parameters. Okay, with me so far? So that's the first step, is to get or compute n values from n input vectors. Okay, what is n? The number of words. N capital is the number of words. N small is the specific word. Okay? Okay? Right. The second step is to get from values to the output vectors. We said that it's just two steps, right? Very easy. From input to values, and then from values to output vectors. Now, from input to values, linear, as we saw in the first step. From values to outputs, here we have what we call the self-attention weights. Now, really pay attention here with this equation. This is the output vector for the word number n. Okay, so self-attention of xn, which is the output vector for that word. This is a summation from 1 to n capital, which means it's summation over all words. Okay, all words. Didn't we say that any word should be attending with different weights, with different percentages to different words? So the output will be a weighted sum of all the value vectors. Vm is the vector for the word number m, and we are doing the sum over m from 1 to n. Okay, so if forget about this term. Okay, assume that this term is not there. Okay, so that means that it's the sum over all vectors, right? It's like summing all the value vectors. What are the value vectors? The ones that we got from here, from step 1. Okay, the ones that we got from step 1. Taban, it's not just the sum of them. It's a weighted sum of them. So if one word is very related to, let's say, the word number 3 is very related to the word number 1. So the weight that is multiplied by the vector, the value vector of the word number 1 should be high. And the weight for other words should be low. So it's a weighted sum over the value vectors. So A here, don't be confused here with A, because we used to use it as an activation function, right? This is not an activation function here. This is what we call the self-attention weight. For each pair of words, n and m, there is one scalar value. It's a weight, it's a number. Okay? That is high if the relation between these two words are strong, or is strong, and low if the relation is not. If a word is attending to another word, then this relation is strong, of course, so the weight should be high. Okay? We will have a visualization for that, so I hope that the understanding will be much better next slide, inshallah. But these are the two steps. So the first one is about sharing, and the second one is the actual self-attention. Because now word number n is attending to every other word, but with different weights. And these weights can be 0, by the way. And some of them can be 0, which means that it doesn't actually attend to these words. But some others, the weight will be higher than 0. Okay? Let's see this in a more visualized way. Of course, weights depend on the input themselves here. You can see that the weights here are a function of the words, pairs of words in the input. Let's visualize this. This is an example where we have a sentence of 3 words only, just to have a simple example. So we have 3 words, x1, x2, x3. x1 is represented by an embedding vector of length 4. So D here is 4. Okay, and how about n? N capital 3. We have just 3 words. Okay, type. What you see here is the 2 steps actually. The first step is getting from inputs to values. How we do that? By the linear layer, right? So it's just like a fully connected layer that is that takes the input vector and produce an output vector, but here we call it a value vector. Okay? And remember that these connections are exactly like these connections. These are not different connections. They are not different weights. They are exactly the same weights. Okay, and of course they are learned. So these are parameters. So we convert x1 to v1, x2 to v2, x3 to v3, but using the same weight matrix, the same bias vector. Okay, that's step one, getting from inputs to values. Now, getting from values to outputs, this is a weighted, so here we are getting the output for the first word, self-attention of x1. It's a weighted sum of all the value vectors. It's 0.1 times v1 plus 0.3 times v2 plus 0.6 times v3, which means that this word, word number 1, attends much higher to word number 3 than word number 2 than word number 1, than itself, actually. Just an example. It might happen. It might happen. يعني the word it مثلا here, why should it attend to itself, right? It should attend to others. Okay, it can happen. Okay, but the idea is the self-attention vector, output vector, is a weighted sum of all the input vectors or the value vectors? The value vectors. The value vectors. Okay. طيب, what do you mean by weighted sum? And when we have when we say that SA of x1 equals 0.1 of v1. V1 is a vector, right? It has 4 values here, right? Right? It's 0.1 times this plus, so this is what? This is v1, right? Plus 0.3 times what? v2. 4 values here. Plus 0.6 times v3. So actually this is a vector طبعا, right? Type. Now when we say weighted sum like that, that means that this value is computed how? This value is 0.1 times this value plus 0.3 times this value plus 0.6 times this value, right? Right? So this value depends only on these 3 values. How about the second one? Same. It depends on these 3 values. And so on. Okay, so that's the weighted sum. So eventually it will be this vector, this whole vector, is a weighted sum of these 3 vectors. Okay, right. Notice 2 things here. The values are positive. I mean, not the values. The weights, the value of the self-attention weights are positive and sum to 1. Okay, which is intuitive, right? We want to get like a mix of all the words. Okay, and that mix should add to 1. Okay, so that the values don't explode. Okay, is that clear? Right. This is for the first output. How about the second one? The second one will have also a weighted sum, but it doesn't have to be like the first, right? So the weighted sum here is 0.5, 0.2, 0.3. This word attends to the other words this way. The third one will have another set of self-attention weights. Okay? Is that clear? So that's the 2 steps that we discussed. The first one is converting the input vectors to value vectors, and then from value vectors to self-attention vectors, or the output, the final output. This is actually the final output. This one, this one, this one. Final output of what? Of the self-attention part. Okay? Forget about the transformers. We'll talk about transformer later. Okay? But this is part of the core part, actually, of the transformer. Type. Let me show you this in terms of relationship. So again, from inputs to values, as you see here, it's very similar to a neural network, right? It's a one layer of neural network, right? You can see fully connected layer, right? For x1 separate from x2, separate from x3. But if you look at the colors here, the colors here indicate the values, the actual values. Okay, you can see that this set of weights are exactly like this, which means the weights are shared. The weights are shared among the input words, the input vectors. Okay. So if I want to represent just this part, this conversion from input to values by a matrix, I can look at here. Okay. This full matrix represents the relationship between the inputs and the values. Value number V1 only depends on X1. V2 depends on X2. V3 depends on X3. Right? Okay? Right? It's a linear transformation for each word separately. And you can see that the colors here are repeated, right? Which means the values are actually repeated, which means that this is one matrix actually, or one submatrix, which is omega here. It's shared among all of them. And this empty cells means it's like zeros, and there's no relationship. Okay? Do you understand this matrix, this big matrix? طيب. Now let's look at the other step, which is the getting outputs from values. Remember when we saw the weighted sum of the vectors, we said that the first one, this one, depends on what? This is the first value of each of the value vectors, right? You can see that the connections are coming from this one, and this one, right? It's like now we want to see it as a neural network, but it's no longer fully connected. It is actually a neural network, by the way, but it's not fully connected. And sometimes even the connections are shared. Okay? And if you can see, no, if I will be, if you can see this one, it gets connections from where? From the second one everywhere. From this one, second one in the value vectors. From this one, and this one. Right? Type. If you compare the colors of the connections going to the red one and going to the green one, these are the weights. They are exactly the same because it's the same weights. Remember here when we did it like that, it's 0.1 is multiplied everywhere here, 0.3 multiplied everywhere here, 0.6 multiplied everywhere here. Okay, so when I compute this one, it's 0.1 times this plus 0.3 times this plus 0.6 times this. So 0.1 and 0.3 and 0.6 are shared. So the values here, the values of the connections that are coming to the first one is exactly the same like the second, exactly the same like all of them. Okay, because it's the same weights. Okay, so this visualization is just showing you that this can be represented as a neural network, but it's no longer fully connected. There are connections that are missing. Okay, and we saw this here because of all of these empty cells, and also here. This is, by the way, transforming from values to outputs. And you can see that again. Let me change the color, or maybe we do it for the second one. So, oh, sorry. I want to show you this. So let's look at this row. Okay, this row represents the second value, the second element of the first output vector. Okay, this one depends on the second element of V1, the second element of V2, the second element of V3. Right? All the other connections are zeros, are missing. They are not there. Okay, they are not there. If this would be fully connected, that would be 4 times 3, 12 times 12, 144 values, right? How many values we have here? How many connections? Much less. Okay, and the different values are just 3. They are repeated. It's just 3 values that are repeated, right? We know, we said 0.1, 0.3, 0.6, right? They are repeated, okay, but the connections are 3 connections are going to each of the output nodes. Okay, so this is just showing you that it's still a neural network, but with so many missing connections, which means that it has less or more parameters. Less parameters طبعا. zeros دي خلاص, there are no weights here. Okay, the weights are much less than a fully connected layer. Now the main question is how to compute the self-attention weights. Now we didn't say how we get these weights, just 0.3, 0.1, 0.6. How did we get these weights? Okay, in 1 minute I will just tell you the first few steps of doing that, and then inshallah we'll continue next time. The first step of computing the weights is that we generate from the inputs what we call queries and keys. Remember that we generated values from the inputs, right? We will also generate queries and we generate keys in very similar way using a weight matrix, but a weight matrix that is specific to the queries and a third weight matrix that is specific to the keys. So it's like we are starting from the input vectors. We will get 3, for each input vector, we'll get 3 different intermediate vectors: values, queries, and keys. The queries and keys, we will use them to compute the self-attention weights. And then we apply these self-attention weights to the values to get the final output. Okay, this is the story that inshallah we will discuss next lecture. Okay. Assalamu alaikum wa rahmatullahi wa barakatuh.